Marhaba. Okay, in this video we want to keep developing our logic that we started with the predicates. Remember, we defined what is a predicate, and a predicate is a descriptive statement involving some variables, and when we substitute a value for these variables, we get a proposition, and the proposition is a statement which is true or false, but not both. And remember, always when we have a predicate, we have on the side a domain from which we choose the values of the variable. Okay, we want to talk about quantification today, but remember that we use quantification in our normal language, in our natural language, for when we want to talk about the quantity or the number of objects satisfying some property. Okay, so we use words in English language, for example, such as all, none, some, and few, every. Okay, so we all of these words represent some number or some quantity of objects. Now, for example, we can say all birds have wings. We can say some people are trustworthy. So you see, we use these quantification words to talk about the number of some objects having a property. Okay, so we want to do this in our logic, but we will use only two types of quantifications. One called universal quantification, and the other is called existential quantification. Okay, so let's explain this in details. First, let P of X be a predicate. Okay, so remember what do we mean by this? So P of X is a statement of the form X has property P. Okay. So remember, a predicate is a descriptive statement which has a variable X, and it says, remember from the English language, that the predicate part of the statement is the part which tells us the property of X. Okay, so we talked about X is a prime. Okay, remember, this is a predicate. It's a statement which says that X, the subject, has the property of being prime. But the property can be any property whatsoever, so let's call it just property P, capital P. Also remember, in our definition of the predicate, we assume that there is a collection of elements or values from which we choose values for X. Okay, so for example, we can say the elements here are 1, 2, 3, 4, 5, 6, 7, 8. Say this is the domain of X, of the variable X, then this means that when we want to substitute a value for X, we can choose it from here. So if we choose X to be 5, say, then our statement will be 5 has property P. And in this case, in the definition of the predicate, we said when we substitute a value for X, the resultant sentence should be a proposition. Okay. Now, quantification gives us another way of making a predicate into a proposition. Okay, so how we have a predicate. I just want to clarify, and we can make it a proposition in two ways. Either substitute a value for the variable. So if you substitute a value for X, it will become a proposition, or quantify the predicate. And this is what we want to explain today, how we quantify predicates. Okay, the first method of quantification, it's called a universal quantification. Universal quantification of, so we do the universal quantification of the predicate P of X. So what is the universal quantification? It's a statement. The universal quantification of P of X is the statement for every element in the domain, for every element x in the domain, okay, we have that p of x is true. Okay, so this is a statement. It's a proposition, by the way, and because it's a declarative statement, it says every element in our domain. Okay, so here is, say, our domain. Say we have 3 elements. It says the universal quantification of p of x. By the way, it is denoted by an upside down a, and then this is x. We read this as for all x, p of x. So this is our notation for this whole sentence. Okay, so to say that for every element x in the domain we have that p of x is true, we write it in this way, and we read it as for all x, p of x. Okay, now this is a proposition. Since I'm saying it's a proposition, I need to tell you when do we consider it true and when do we consider it false, because a proposition is either true or false, but not both. So for all x, p of x is true if, as it says, if every element in the domain, so say we have only 3 elements, a, b, c, if every element in the domain has property p. So you look at a, it has property p, you look at b, it has property p, whatever is this property, and you look at C, it has property P. If every element in my domain has property P, then we say for all x, P of x is true. Okay? So this means when for all x, P of x is false when not every element in the domain has property P. For example, say this is the domain. Again, it has 3 elements. And suppose A has property P, B has property P, but C does not. Since not every element in the domain has property P, in particular C doesn't have property P, then this we say for all x, P of x is false. Okay? So again, to repeat, we start with a predicate, we construct a new sentence which we call the universal quantification of the predicate p of x. This is a proposition, and what is this proposition? It's the following statement. For every element x in the domain, we have that p of x is true. And it's true if every element in the domain has property p. It's false if we can find at least one element or more without the property p. Okay, so we'll have examples, but let me introduce the second type of quantification. So this is called existential quantification of the predicate. Sorry. Okay, existential quantification Okay, so this is called the existential quantification of the predicate p of x. Okay, what is this? It is the statement which says there exists some x, some element in the domain, okay, such that p of x is true, which means such that x has property p. Okay, so this is the existential quantification of p of x. This is the statement: there exists some x in the domain such that p of x is true. Okay, let's discuss. This is a proposition. Let's see. Okay, first let me tell you how do we represent it. We represent it by an inverted E letter. Okay, so there exists an x, P of x. Okay, so all this statement is expressed as in these symbols. This is read as there exists an x such that P of x is true. And this statement is true. Again, suppose this is the domain we have, A, B, C. Suppose A doesn't have property P, B has property P, C doesn't. Okay, in this case we declare this statement to be true. Why? Because all what it says is there exists at least one element in the domain with property P. And yes, there is at least one in this example, it is B. Okay, now there exists x, P of x is false if you look at your domain and you check every element to see if it has property P and you can't find anyone. So there is no element in your domain. So say we have three elements, A, B, C, none of them has property P, and so there exists x, P of x is declared to have the truth value false. Okay, now let me just say one thing, that this letter, this symbol is called the universal quantifier. Universal quantifier. And the other symbol, the inverted E, is called the existential quantifier. Okay, so let's have examples on quantification of predicates. Okay, so first example, suppose the predicate P of x says that x plus 1 is strictly bigger than x, and suppose the domain is the set of real numbers. So this means that you can choose any real number to be the value of x. Now let's discuss, is for all x P of x is true. So this is true when every element, so what is our domain? This is the real number line. Okay, you go and check every element in your domain. So say here we chose 2. Is it true that P of 2 true? What is P of 2? That 2 plus 1 is bigger than 2. So x plus 1 is bigger than x. When x is 2, then we get 2 plus 1 is bigger than 2. Yes, it is true. Now you go and check it for 4. Is P of 4 true? Is 4 plus 1 bigger than 4? Yes, 5 is bigger than. You go to negative 10. Is P of negative 10 true? Like negative 10 plus 1 is negative 9, which is bigger than negative 10. So yes, it is true. Try to check it for every real number, and you see that every real number has the property that if you add 1 to itself, you get a number bigger than itself. So this is true proposition, because every element in R in the real numbers has the property P, and what is the property P is, so x has property P if you add 1 to x, you get a number bigger than x itself. Okay, let's discuss the existential quantification. There exists x, P of x. Is this true? Well, yes, it is true, because, okay, what does this say? This is true if you can find one element, just one, at least one, which has property P. Is true because just choose any real number, because P of 8 is true. Why P of 8 is true? Because 8 plus 1 is bigger than 8. Okay, since we found an element in the domain which has property P, then we declare there exists x, P of x to be a true proposition. Okay, let's have another example. Okay, now let's look at the predicate Q of x. And Q of x is the statement x is strictly less than 2. And again, the domain is the set of all real numbers. We can represent it by the real number line. Now, again, what is Q of X? It's a predicate which says X has property P, but what is, sorry, X has property Q. So you can read this as X has property Q. And what is property Q is that being less than 2. So you can also see that Q of X means that X is less than 2. Okay, so this is the property, that you are being less than 2. Okay, so now what do you think? Is for all X, Q of X, is it a true or false statement? It's true if every element in the domain is less than 2. So here is 2. And we look at all the elements in the red shaded part, because these are then all the numbers less than 2. Now, this means that not every element is less than 2. For example, just choose 5. Okay, so this is false, so this statement is false because not every element has property Q, in particular Q of 5. So what's Q of 5? Q of 5 says that 5 is strictly less than 2. So this statement is false. Okay, so the universal quantification is false because not every element in the domain, in our domain, has property Q. In particular, 5 doesn't have property Q, and we call 5 in this case a counterexample to the universal statement for all x q of x. So this is called a counterexample. Okay, now let's see, do you think there exists x q of x is true or false? So it is true if you can find at least one element, just one, in the domain which has property q. Well, we can find one. 0 is less than 2. So it's true because q of 0 is true. Okay, let's have let's have another example. Let's look at the predicate p of x, which says it is a statement which involves the variable x, which says that the square of x is bigger than or equal to x itself. Okay. Notice that we want to discuss the statements for all x p of x, and there exists an x p of x. I want to emphasize now in this example that the truth value of these statements depends on the domain. Okay, maybe this statement is true in one domain but false in another domain. Okay, so the truth is dependent on where we are evaluating the statement, in which domain we are evaluating it. Okay, so let's consider these two statements in two different domains. The first domain, when the domain is the set of real numbers. Okay, clearly, what do you think? Is it true that for all x in the real numbers, is it true that for every real number x we have the property p, namely that the square of x is bigger than or equal to x? Well, this is false because it's not true for every real number. In particular, p of half is false. I mean that half doesn't have property p because half squared is not, which is quarter, is not bigger than or equal than half. Okay, right? P of half says that half squared is bigger than or equal to half, but this is false. Okay, so not every element in the real numbers has property p. However, there exists x p of x is true because we can find a number. So, for example, is true. This is true because p of 4 is true. Why? Because 4 squared is bigger than or equal to 4. This means that 4 has property P, and this statement, says there is at least one element with property P, and yes, there is an element, namely 4, for example. So it's a true statement. Now, let's check it in this domain, in the set of positive integers. So 1, 2, 3, 4, 5, and so on. So let's check, is this statement true or false in this domain? Well, this is true if every element has this property. Let's check. Does 1 has property P? P of 1 is true because 1 squared is bigger than or equal to 1. P of 2 is true because 2 squared, which is 4, is bigger than or equal to 2. P of 3 is true because again 3 squared, which is 9, is bigger than or equal to 3. You can check that every single element in our domain has property P, and this means that for all x, P of x is true because every element has property P. Of course, there exists x, P of x is also true here because 3 has property P, for example. Okay, so because there is an element with property P. Okay, let me give you another example. So see here, this statement, so for all x, P of x is false in the real numbers when the domain is the real numbers, but it is true when the domain is positive integers. Okay, let's have another example of this kind. Okay, look at the statement. So let S of x, consider the predicate S of x, which says, so x has property S if the square of x plus 1 is equal to 0. Okay, again, an object x has property S if you square it and add 1, you get 0. Now, suppose first that the domain is R. The domain is real numbers. The question is the statement there exists an x, S of x, is true or false? So what is this statement? There is at least one element x in the real numbers such that x has property S. Okay, well, the answer is that this statement is false in the real numbers. Why is this? Because suppose we have a number x with this property. Let's see that we can satisfy this property. If you have a real number x and you square it, then this number is 0 or positive. Now, if you add 1, then this result is always bigger than or equal to 1 because we are adding in a 0 or a positive value to 1. So this new value will be 1 or more, and 1 is strictly bigger than 0. So we will never hit 0 no matter how you searched for a real number. Whenever you square it and add 1, you will be always away from 0. Okay, so this is false. However, when the domain is complex numbers, then we can find an element with property S. Okay, so in the complex numbers, this statement is true. Why? Okay, think which complex number have the property that if you square it and then you add 1, you get 0. It's true because S of I, where I is the imaginary number, which has the property that its square is -1. So S of I is true. Why S of I is true? Because I squared plus 1, I squared by definition is -1 plus 1, which is 0. So in the complex numbers, Okay, in the complex numbers, we can find a number that we square and then add 1, we get 0. This means that this statement, there exists s of x in the complex numbers, is true. Because there is an element in the complex numbers which satisfy the property S, namely I. I is the witness of this sentence. Okay. Now let's have a final example where the domain is a finite. Like all the examples we had above were infinite domains. Okay. Suppose the domain in this example is the set containing just 4 elements, 1, 2, 3, and 4. And I ask and look at the predicate P of x, which says that x squared is strictly less than 10, and look at the predicate Q of x, which says that x squared is strictly bigger than 10. Let's examine the statement for all x p of x. Is it true that for all x, let me use the red color here, is it true that for all x p of x is true or false? So note, what does it mean that for all x p of x? It means that in every element in my domain has property p. So I want to say that this is logically equivalent. It has the same meaning, the same truth value as saying that 1 has property p, so p of 1, and 2 has property p, and 3 has property p, and 4 has property p. So for all x p of x is true when every element in the domain has property p. But we have 4 elements, so this says that 1 has property p, 2 has property p, and so on, and 3 has property p, and 4 has property p. Well, is it true or false that every element has property p? It's false, because this proposition is false, because a 4 squared is not less than 10. Okay, p of 4 is false because 4 squared less than 10 is false. So remember, what's p of 4? Substitute 4 for x. So we'll get 4 squared, which is 16, is not less than 10. Okay, now let's analyze there exists x q of x. So what does it mean there exists x q of x? It means there is at least one element in the domain with property q. So either this element is 1, so q of 1, 1 has property q, or 2 has property q, or 3 has property q, or 4 has property q. Okay, now is it true or false, this one? So let's see, does 1 have property q? So is 1, here is property q. Is 1 squared bigger than 10? No, so this is false. Is 2 squared bigger than 10? 4. 2 squared is 4, 4 is not bigger than 10, this is false. 3 squared, is it bigger than 10? No, 9 is not bigger than 10. So now q of 4 is 16 squared, which is bigger than 10, and so this is true. Now false or false or false or true is true. So this thing is true. Okay, this is one way to see it. Another way to see it, why there exists xq of x is true, because it is true when there is at least one element in the domain with property q, and yes, this element is 4. 4 has property q. Q of 4 is true because 4 squared is bigger than 10, which 16 is bigger than 10.